Hi, I'm Jonathan Aldrich. Let's continue talking about dynamic semantics, this time with variables and statements. Again, we'll take a formal approach. Let's consider how to add variables to our semantics. We're going to use a construct called environments. An environment maps each variable to the value that it holds. For example, the environment shown here maps x to 1 and y to 2. We can extend our judgment form to incorporate environments. So this judgment form, e turnstile lowercase e evaluates to v, can be read in environment e, expression little e evaluates to value v. This turnstile symbol means that the evaluation judgment on the right is true, assuming the environment on the left. Now we can define a rule for variable evaluation. What does the variable x evaluate to? Well, we'll use a premise, and that premise will look up the value of x in environment E. So, for example, if our environment maps x to 1 and y to 2, if we look up x, we get 1. If x is not present in the environment, then the premise e of x equals v is not true for any v, right? There is no x in the environment. And so the variable does not evaluate to any value at all. We say that if we try to look up the value of some variable and it's not in the environment, we say evaluation is stuck. That's a simple way to model errors. So if you use a variable before it's defined, that would be an example of the semantics getting stuck. And maybe we want it to get stuck, right? Because that's not a valid program. Or at least it's a program with undefined behavior, even in a language like C. Other errors are possible too in our semantics. For example, if you look at the ev float rule from our last lecture, the argument has to be an integer n, not a real. And so if you call ev float, if you call float and you give it an argument that's already a real, then our evaluation rule would not work, right? Because the premise that requires the argument to be an integer n would fail, and so we could not form a derivation that used that rule. We can take all of our rules to work with environments, because they're going to have to all be consistent. A judgment form always has to be used consistently in all the rules. And so if we add e to some of our judgments, like one to evaluate variables, we have to add it to all of them. And I can see there's a typo here. Apologize for that. We need an e in the evlet rule as well. Generally, these rules don't change the expression e because we're just evaluating expressions. We're not assigning to new variables yet. We'll see that in a minute. And so when we evaluate floating point conversion, for example, we evaluated some environment e. That same environment e is used to evaluate the sub-expression e that is going to be converted to a floating point number. Similarly, the ev-binop rule takes the expression for evaluating e1 plus e2 and takes that same environment and uses it to evaluate e1 and the sub-expression e2 as well. Now, how do we actually get variables into the environment? Well, we'll use statements to assign variables to values. So let's add statements to our calculator language so we can do assignment and we can declare variables as well. And we'll also provide some reads and some writes. So now our abstract grammar has integer declarations and real declarations. Those are just int x and real x. We have assignments, x gets e. That could be either for an integer variable or a real valued variable. And then we have write and read, which read and write to the console. So we'll read a variable into x, or we'll write an expression to the console. Our statements are arranged as a kind of linked list. So every statement form has a first part, and then a second part is the continuation of the statements. So after int x, then we have the statements, and then x will be in scope in those statements. After x gets e, then we have the statements afterwards, which will see the new value of x. Because it's a linked list, we need a base case, and so we use the empty statement at the end. Of course, a real program won't have the notion of an empty statement. It just ends in a semicolon, in the last semicolon perhaps. Or we use the semicolon as a statement separator, so we don't need it at the end. This is just a matter of formalism. It turns out to be convenient to represent our abstract syntax tree in a kind of a linked list form. So even though we don't parse it this way, it'll look like this in our internal syntax. So let's look at the semantics of a variable declaration. A variable declaration is a declaration like int x, here we're using integer declarations, followed by a semicolon that ends that statement, and then followed by an s, which is another sequence of statements that comes after this. So we're checking this statement or we're evaluating this statement in some environment E1. And because we're declaring x, we'd like to know that x is not already declared, right? Because if it was already declared, maybe as a real number, then there might be some confusion about whether x is a real or an integer. We could override the old value with a new value. That would be a kind of shadowing semantics. But for the semantics here, we're just going to check that it's not already declared, and we're going to say it's an error if you declare a variable that's already declared. So to do that, we have this notation that x is not in the domain of E1. What this means is that we're checking whether x is a key of the environment E1 or not. The domain is, or DOM for short, is the set of keys in this environmental mapping. So by saying x is not in DOM of E1, we're saying x is not one of the keys in this environment. It's not something we can look up. For the rest of the statements, we need to extend the environment. And here we will extend the environment with x mapping to 0. I'm assuming a language that initializes variables to 0. And so the notation E with brackets x arrow 0, that means an environment that's the same as E1, but that has an additional entry mapping x to 0. So we construct this new environment that is extended with x, and we evaluate all the other statements in S. And then at the very end, we take out an expression E2. I'll explain that in the next slide. But there's a similar rule for declaration of variables of type real that looks all the same, except that we'll initialize x to 0.0. Why do we have an E at the end of this judgment? So our statement semantics has this form that starts with an environment E1, has a sequence of statements, and then ends with another environment E2. We read this as, in environment E1, statement S executes and produces a new environment E2. Why do we do this? Well, we want an output environment to capture the changes from variable declarations and assignment that happen in that sequence of statements. And this is how we find out what is the result of a program, right? The result of a sequence of statements is basically what are the new variable values, because statements are executed essentially for their side effect in this little calculator language. So let's look at assignment to see how this works in practice. We're evaluating an assignment x gets E, followed by another sequence of statements. We're evaluating in some environment E1, and we'll start by evaluating the right-hand side of the assignment E to a value of E. Again, we'll use the current environment E1 to do that. Now, we'll check that the resulting value has the right type for the variable E. So the way I've notated this in this rule is to say, let's look up the value of x in the environment E1. Well, let's get the type of that, and let's compare that to the type of the value. And if the types are the same, then this assignment will succeed. We can proceed. And at that point, we're going to produce a new environment that is the same as E1, except that the map for x is updated to now refer to V instead. And so in this new environment, with the updated x, we'll evaluate the rest of the statements in the program S, and we'll get some environment E2. That environment E2 is also the result of this assignment statement followed by the rest of those statements. Let's do a little bit of housekeeping. Remember that our abstract grammar represents statement sequences as a linked list. And so we need a rule for the base case, basically an empty list of statements. The evEmpty rule just takes an empty list and says, if you evaluate this empty list in an environment E, you get back that same environment E, because there's no statements to change any variables in E. Thus, the input and output environments are the same. With this knowledge, we can now construct a derivation that assigns and uses a variable. So we'll evaluate the program int x, followed by x equals x plus 1. We'll add parentheses to our program to show precedence and add an empty statement at the end to match our formalism. So down here is the statement that we want to evaluate. We have a declaration int x, and then the rest of the program is this sequence here that I put in parentheses. It's not usual to put parentheses around programs, but remember we're really describing an abstract syntax tree, so I want to be clear about the way things group up. Here we assign x gets x plus 1, and then at the very end we have the empty statement epsilon. Okay, so we can then go ahead and evaluate this in the expected way, right? We use the evIntDecl rule that I showed you first. We check the declaration by starting by checking that x is not in the domain of the environment. Our initial environment is just the empty environment, so x of course is not in that domain. So we'll add a mapping from x to 0 and evaluate x gets x plus 1. Now, how do we do this? Well, we're going to evaluate the assignment rule. We check that x is indeed in the domain. That's a requirement for assignment being correct. And then we'll check that in the environment where x maps to 0, x plus 1 maps to 1, right? That should be true. That's actually going to be shown up here. So in fact, if I had put this all in one stack, it would have been really, really wide, right? So just as a notation, just to get it on the slide, I wrote this little script D to represent all the derivation that's above here, and then I gave it separately up here. And then we used the dotted lines to kind of make the connection, a little bit more intuitive. So we can now go and evaluate this part. That's actually exactly just expression evaluation, and so we evaluate the variable x down to 0, which is true because we have the environment x gets 0. Similarly, 1 evaluates to 1. That's just the literal rule. The type of 0 is the type of 1. They're both integers, and so we can add them. 0 plus 1 is 1. That gives us the core derivation that tells us the right-hand side of the assignment. We'll also check the empty rule, which just says the environment is not transformed, and so the resulting environment gets used on the right-hand side of all of these expressions, and we find out that the end of evaluating the sequence is an environment where x is equal to 1. To finish up the semantics of our language, we can use some primitives to model read and write constructs. So for read, basically we're going to do some kind of read console operation. This will be a primitive that might be implemented as a library function in the runtime of the language. We take the value, the v that was read in the console, we check that its type is the type of x. Again, we look up x in the environment, figure out its type, and v had better match that. And if that's the case, then we can evaluate the rest of the statements after having read this value from the console. Similarly, if we want to write an expression, we evaluate that expression down to a value, again in the current environment. We invoke write console and assert that it's okay in the sense that it doesn't produce an error or something. Again, some informal notation there, and then we have E1 in the environment E1, we continue to evaluate the rest of the program, producing some E2, which is the final environment for the program. Now, if we wanted to be a little bit more formal about reading and writing, we could have streams of input tokens. So in addition to an environment E1, we could say, okay, here are all the tokens you're going to read as this program executes. Reading x will basically say, okay, I'm going to read E1 of x, and we'll get some value v. We check that the type of v is the type of the first value that we're going to read, and then we evaluate the rest of the program. The rest of the program is going to read v of I plus 1, and so on. And so our new environment will be the same as the old environment, but with x mapped to this first thing that we just read. We then evaluate the rest of the statements. It's possible that those don't use all the values in the input stream, so we could just represent the rest of it here. This is just an example. If you wanted to formalize I/O, there's ways to do it, right? And similarly for almost any construct in the programming language, if you really wanted to model it formally, you can figure out a way to do so. Sometimes for I/O or other kind of operating system level features, we just use primitives, as I've done in the first 2 slides here. Let's talk a little bit about how to go from these dynamic semantics to an implementation. It turns out that our evaluation rules were carefully designed to be algorithmic. What that means is that we can examine the premises in order to find a derivation without ever having to guess anything about that derivation. So let's look at how this would work, using ev binop as an example. So the input to ev binop is conceptually the expression that we're evaluating, E1 op E2, for some operator, right? Well, how are we going to execute this? Well, we can take E1, and we know that's an expression, and the expression is the input to our judgment. Again, I'm going back to the judgment without environments, but the same thing could be done to the judgment with environments. Based on the input of E1, we'll get an output of V2. We'll get an output of V1. And that will be from whatever rules are used to evaluate E1. So always our expressions are going to be the input and the value will be the output. Now we can evaluate E2, which was also an input, down to some value V2. The value of V1 and V2 can be used to look up the type of those two things and check that. And then we can also use them as inputs to mathematical evaluation, where we say v1 plus v2 or v1, whatever the operator is, gives us v3, and finally that's the result. So you can visualize the flow of computation through this rule. And we wrote all the rules, in fact, in a careful way so that this can be true. This is not true of all evaluation rules you'll ever find. We could write a non-deterministic value rule where you say, some expression like random evaluates to any integer at all, right? So there, it wouldn't be a deterministic or algorithmic kind of approach, but of course the intention there is the implementation just picks the n, and so we could use a random number generator, or we could use a source of randomness from hardware that does that. What's nice about this is if we've written our inference rules in this algorithmic way, which is certainly true of the ones we've discussed so far in this lecture, we can translate them to interpreter code. So, for example, this interpret expression function is going to take an environment and an AST. So those are our inputs. In the version of the AST, in the version of the rules with the environment will be an input, and we'll return a value. So we'll case analyze on the AST, and case analyzing on the AST is basically just figuring out which rule do we want to use. In the case of a binary operation, we're going to start by evaluating both subexpressions, right? So we take our interpreted expression, we do a case analysis on the AST-A. If it's a binop, well, that binop will have pieces A1 and A2, sub-ASTs, as well as the operator. We'll call interpret expression recursively. That's equivalent to the premise that is just another invocation of the interpretation judgment, right? We'll pass in our expression E, we'll pass in our A1, and we'll get a V1 value out. We'll do the same thing for subexpression A2. If the type of the two is the same, then we do a case on the operator, and we either return V1 plus V2, V1 minus V2 times, or in this case, that's a typo, should be divided by. So the case on the operator is a little bit implicit in the inference rule. Our notation is just kind of generic on the operation to be used, but otherwise you can kind of basically just read this code off of the inference rule. We can do similar things for other cases, right? So for an integer literal of n, we simply return n. For a real lit, we return r. For a variable, we look up x in the environment E. And then finally, for floating point and truncation operations, for floating point, we'll go ahead and evaluate the subexpression, again in the current environment. We check that the type is an integer, and then return whatever the result of toFloat is, right? That's our primitive. Now, if some of these type check operations fail, then we'll return some kind of an error expression. In this case, we can't apply float to something that's already a real, and so we'll raise an error that says this is already a real. And the code for truncate is similar to the code for float. We can also write an interpreter for statements. Here, instead of returning a value, we're going to return an environment. I'm going to assume the following operations on the environment. We already saw lookup of x and e, but we can also test whether the environment has x as a key. We can extend it, so extend will produce a new environment that adds a mapping from x to v. And we can use update, which takes the environment and updates the mapping of x to be v. So based on this, we can write rules for int_decal. That'll check to make sure that x is not a key already. If there is a key, then that's an error. Otherwise, we interpret the statements that come afterwards in an extended environment where x maps to 0. We can do real decal in a similar way. The only difference is that x will map to 0.0. The floating point equivalent. And then our assignment semantics will first of all make sure that E has the right key, otherwise there's an error. Then it will interpret the expression to get some value v. It'll check that that value has the right type. If not, there'll be another error. And then we'll interpret the rest of the statements. But we'll update the environment E so that x maps to v. Now our environmental updates could be implemented in a couple of different ways. We could implement them functionally. So maybe the environment is just a linked list, and we append something we add something to the front of the linked list so that we can then look up that variable. We could also do an imperative implementation where perhaps this environment mapping is a hash table, and we're adding something to the hash table or updating it. Imperative update is usually more efficient, but you can use either approach, and certainly there are efficient functional data structures that can do almost as well as something like a hash table. Let's check our understanding.